Happy to see you, students. Today, we are going to see the topic of interference with polychromatic light. When a polychromatic light, which means white light, a white light is used in interference experiment. Colored fringes of varied thickness will be formed on the screen. This is because different colors having different wavelength. We know very well the colors will be varies its color, definitely its wavelength will be different, which means varies. However, the central fringe or a zeroth fringe will always be in bright and white in color, because all the colors falling on the point at O will have no path difference. Once again I repeat, at the center point O, all the colors will be falling. So in the point of O, they have no path difference, which means zero path difference. Hence, in center path produces only in constructive interference is possible at the point of O for all the colors. Next topic, interference in thin films. Interference in thin film. Let us consider a thin film of a transparent material of a refractive index mu, and its thickness will be small d. A parallel beam of light will be incident on the film at the angle of I, which means angle of incidence will be I. The wave divided into two parts, which means upper surface and one is reflected. The reflection process occur in the upper surface. In another, a refracted part, which means a lower area. When the refracted part which enters into the film and again get divided at the lower surface. Once it's transmitted out, the film of the other reflected is back into the film. Reflected as well as refracted. So the waves sent by the films of multiples reflection and refractions will be occur inside of the thin film. So the interference will be produced by both reflected and transmitted light. A simple nothing but when the incident light will be fall on the thin film which is parallel, the incident light must be produced of reflected and also refracted. The refracted ray reaches at the bottom of the thin film at point B. One of the wave is transmitted and another one is again refracted inside of a thin film. So same process at the point the refracted which means the reflected ray passes at the upper region of the thin film. Once it's get reflected and refracted. So the reflection and refraction takes place inside of a thin film. So first of all, we can find the transmitted light like as BDF. So first of all, the light transmitter may interfere the produce of result in intensity. Let us consider the path difference between the two waves transmitted from B and D. So the two waves move together and remain the phase up B was splitting. The extra path traveled by the transmitted wave at the point of D inside the film, which means BC and CD. So adding the path of BC plus CD, we know the value of the thickness of the thin film is D, small d. So if we approximate the incidence on the normal which means I equal to 0, then the point of B and D are very close to each other. So the extra distance traveled by the wave approximately twice of its thickness, which means whereas BC plus CD becomes D plus D equal to 2D. An extra path is traversed in the medium of refractive index mu. The optical path difference whereas del equal to 2 mu d. For the conditions of our construction interference, we can write as 2 mu d equal to n lambda. This is a constructive interference for transmitted rays. Similarly, we can write as destructive interference for transmitted rays 2 mu d equal to 2n minus 1 into lambda by 2. This is an destructive interference for transmitted light. We have only see about the transmitted light, which means BDF. And also, so the same way we can find as a reflected light. And experimentally and also theoretically proved that the wave while traveling into a rarer medium to denser medium. This is a rarer medium, this is a denser medium. So light getting reflected by a denser medium undergoes phase changes will be phi. The light enters to rarer medium to denser medium, so it means undergoes the phase change of pi. So additional path difference is lambda by 2 will be produced as be considered as. So the path difference between the light waves reflected by the upper surface A and other way coming out at the region of C, the passing through the film. So additional paths, the same way additional path traveled by the wave coming from out of at the point of C. So the path inside film AB plus BC. So nearly the normal incidence of the distance could be approximated as AB plus BC. So AB and after BC becomes D plus D equal to 2D. So the extra path traveled in the medium of refractive index mu. The conditions for constructive interference the same way. Condition for constructive interference 2 mu d plus lambda by 2 equal to n lambda, or otherwise we can write as 2 mu d 2n minus 1 into lambda by 2. This is a condition for constructive interference by the reflected ray. The same way we can write as the additional path difference lambda by 2 and phase change phi in rarer to denser reflection taking place at the point of capital A. The condition for destructive interference for reflected ray 2 mu d plus lambda by 2 equal to 2n plus 1 lambda by 2, or 2 mu d equal to n lambda. This is a condition for destructive interference. Next, we are going to the topic of diffraction. So diffraction is a general characteristics of all types of waves like sound wave, light wave, in water, etc. So diffraction is the bending of waves around the sharp edges into the geometrically shadowed region, which means let us consider the surface of the water surface, the region of water surface. This is an obstacle. When we have put a stone inside of a water, the waves will be produced like these formations. Once it reaches the obstacle, the wave will be produced in forming of bending of the surface of the water. So this is called as diffraction. This is a violation of the rectilinear propagation. Rectilinear propagation is linear propagations, which means diffraction is opposite of rectilinear propagations of light. We have studied in ray optics which says the light should be travel in straight line in a medium without bending. Okay, but the diffraction is prominent, which means prominent means important one. Prominent only when the size of the obstacle is comparable to the wavelength, which means the diffractions will be occur when the wavelength of the light in obstacles will be comparably equal. So only the conditions will be diffractions will be produced. This is the reason why sound waves get diffracted prominently by the obstacles like doors, windows, buildings, and etc. The wavelength of the sound waves is large and comparable the geometry of these obstacles. But the diffractions in light is more pronounced when the obstacle size of the order of the wavelength. Only one the reason the diffractions will be occur where the obstacle size of the obstacles in the wavelength will be comparably equal. Only the diffractions will be occur. Next topic, diffraction at a single slit. This is on a diagram. This is on a converging lens. We are using of two lenses like us, namely L1 and A2. Converging lens means is nothing but convex lens. Okay, a parallel beam of light falling normally on the slit of AB, having a width. The diffracted beams falls on the screen kept at a particular distance, capital D. The center of the slit. Here C be the center of the slit. A straight line passes through the slit C in perpendicular to the plane of slits meets at the point of the screen will be O. We would like to find the intensity of the point at any point of P on the screen. The line joining of P in different points on the slits can be treated as the parallel line, so making an angle with theta normal to C O. All the waves to start parallel to each other from the different points of the slit interfere the point of P at the point to give the resultant intensities. The point P is geometrically shadowed with the central is maximum to spread due to the diffraction. We need to give the conditions for the point P various minima. So the basic idea they're divided into much smaller than the even number pairs, then their contributions we can apply the point of P will be proper path difference in the show the destructive interference takes place at the point of minimum. So we can divide the 2 point explaining by maxima and minima of the slit will be divided into 2 parts, the number of parts. So first conditions we have find the central fringes at point P to be the first minimum. So let us divide the slit AB into 2 halves like this, EC and CB. This is the diagram, AC and CB. So now the width AC is divided by 2. Now the width here. Now the width AC is divided by A by 2. We have different points on the slit which separated by the same width, and also CB by we can write as A by 2 corresponding points of the condition for P to be the first minimum. The path difference of the light waves from the different corresponding points meeting at the point of P, which means screen, and interfere destructively to make the first minimum. The path difference between the waves from these corresponding points, which means here this point, this is an theta, whereas B and B the path difference, so we can write as sine theta equal to opposite side, then after hypotenuse, here it is hypotenuse, so we can write as opposite side we can write as the name of E, and the path difference del we can write as del equal to E by sin theta. Alternative method. The same method we can apply this first minima conditions, del A by 2 sin theta, then A by 2 sin theta equal to the first minima of lambda by 2. Here 2 can be neglected, so A sin theta equal to lambda. This is the first minima for the conditions for P. So conditions for second minima, we can apply the value of 2 in bottom of. So let us divide the slit AB into 4 ports. So with the width of A by 4. First of all A by 2, then second one A by 4. So which are separated by the same width A by 4, the path difference del between the waves corresponding points del equal to A by 4 sin theta. In the condition for P be the second minima A by 4 sin theta, and then after lambda by 2. So 2 cancel here, A by 2. So multiplying these sides to quote is here. So A sin theta equal to 2 lambda. This is a second minimum. In finding the value of third order minimum, so we can write as the same way the slit is divided into 6 equal ports. So explain the conditions for P. Be the third minimum is A by 6 sin theta equal to lambda by 2. 1 3 2s are 6, in 1 2s are 2. The 3 can be multiplied to the value of wavelength lambda. So we can write as A sin theta equal to 3 lambda. And finally conditions for nth order minimum. The dividing slit into 2n number of even number equal ports make the light produced by one of the corresponding points to be cancelled by its center ports. So that's the condition for nth order minimum. A by 2n equal to sin theta into lambda by 2. So 2 can be neglected, the n can be multiplied here. So A sin theta becomes equal to n lambda. This is the condition for P to be the first minimum. So next we can find the value of maxima value. For maxima, the points, the slits to be the divided in odd number equal ports of one ports remains in the uncast by making the points of upper bright. So 3 5 7. The first maximum A by 3 sin theta equal to lambda by 2, we can write as multiplying the 3 here into this. So A sin theta equal to 3 by 2. The same way conditions for second maxima. A by y sin theta equal to lambda by 2. So A sin theta becomes 5 lambda by 2. And the condition for third maximum is A by 7 sin theta equal to lambda by 2. So we can write as A sin theta equal to 7 lambda by 2. So finally in nth maximum we can write as A sin theta equal to 2n plus 1 lambda by 2. Here n, the value of becomes 0 1 2, so put the value of n 0 1 2 3 is the order of the diffraction maximum. So clearly tells us the central maximum is called the 0th order is maximum. The points of the maximum intensity of light nearly midway between the successive minima. Next topic, Fresnel distance. So Fresnel distance is a distance up to which the ray optics valid in terms of rectilinear propagation. Rectilinear propagation is a linear straight line propagations. We know that diffraction, as there is a bending of the light, is called as diffraction. The rectilinear propagations is light is y-directed, which means opposite. But this bending is not significant till the diffraction ray crosses the central maximum and the distance is it. So Fresnel distance is the distance up to which the ray optics obeyed and beyond which the ray optics not beyond out by the wave optics becomes zigzags obeyed. So the first conditions, we know that from the diffraction equations, the first minima equal to sin theta equal to lambda by E. the value, the theta will be becomes very small, so sin theta becomes theta, so theta equal to lambda by a. So the second case, same way, from the definitions of Fresnel distance we can write as sin 2 theta equal to a by z. Here theta will be very smaller, so we can write as sin 2 theta becomes 2 theta, so a by z. We need the value of theta because of the both the equations, diffractions and Fresnel distance, both are left hand side same, so we can replace as convenient our, so lambda, so here it is theta equal to a by 2 z, so both our left hand side will be same, so equating right hand side, and lambda by a equal to a by 2 z. So after rearranging we get the Fresnel distance z, a into a squared into lambda. This is in the Fresnel distance. And next topic,